The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. There are two different classes that may be observing this session. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmail@ybcc.edu and I'll respond as soon as I can. All right, so today we're going to start chapter 11. We're going to begin in section 11.3. And so let's go ahead and get started. Previously, we have looked at linear equations. An example might be y equals 2x, the graph of which is a straight line. We've looked at quadratic or second degree equations, such as y equals x squared, the graph of which is a parabola. Today, we're going to look at a new group of functions, equations, that are called exponential equations. And they are in the form such as, for instance, y equals 2 raised to the x power, where the exponent is the variable. All right, we're going to switch to a different screen. So I'm going to pause the recording. So here we have the graphing screen, and we're going to look at an example of an exponential equation. The first one we're going to look at is y equals 2 to the x power. All right, so let's make a table of values. And I'm going to let x go from -3 to +3. So let's see what we get. If x is -3, y equals 2 to the -3 power. Recall that we can rewrite a term with a negative exponent by writing it as 1 over that same base to a positive exponent, which becomes 1 over 8, or 1/8. Y equals 2 to the -2 power would be 1 over 2 to the +2 power, or 1/4. Y equals 2 to the -1 power is 1 over 2 to the +1 power, or 1/2. Y equals 2 to the 0 power. Recall that a base other than 0, any other base raised to the 0 power, equals just 1. Y equals 2 to the 1 power is 2. Y equals 2 to the 2 power is 4. And y equals 2 to the 3 power is 8. So plotting these points, we get, let's see here, -3 1/8 is approximately there. -2 1/4 moves up a little bit. -1 is up to a half. 0 1 1 2 2 4 and 3 8. So we get a graph. Let's see here if I can draw a decent curve there. Maybe. Trying to match. Let's see here. Yeah, that's close. This continues on, and this continues on in that direction. So this is an exponential equation. It's also a function. Notice that it passes the vertical line test. Okay. It has no x-intercept. It doesn't cross the x-axis. It has a y-intercept at 0, 1. And we say that it is increasing over its entire domain. As x gets larger, y gets larger. In fact, its domain would be all real numbers, but its range would just be greater than 0. So going to the left, this extends, getting closer and closer to 0. Going to the right, this extends, heading on up to infinity, but the domain is all real numbers. But again, the range is just greater than 0. All right, let's take a look at another example. Let's take a look at y equals 3 to the x. And let's put that on the same graph here. So let's switch to a different color. Let's go to blue. So we've got y equals 3 to the x power. And let's see here. I'm going to use the same x values. Wait a minute. Let's go back to the red equation for a minute. There's something going on here. I think in parabolas we had the same y value, you know, two different x values, but what's the relationship here? Well, every time x increases, y doubles, and we've actually got sort of a reciprocal relationship here and here and here. All right, but 2 to the x, every time x goes up by 1, the y value doubles. So let's see what 3 to the x does. If x is -3, y equals 3 to the -3 power, which is 1 over 3 to the 3rd power, which is 1 over 27. If x is -2, y equals 3 to the -2 power, 1 over 3 squared, which is 1/9. If x is -1, y equals 3 to the -1 power, 1 over 3 to the 1, or 1/3. 3 to the 0 power is 1, 3 to the 1 power is 3, 3 squared is 9, 3 cubed is 27. So again, we've got sort of that same reciprocal relationship going on, but now the values are tripling. So when x is -3, y is 1/27. When x is -2, y is 1/9. X is -1 is 1/3. 0, 1, 1, 3, 2, 9, 3/27. So what's going on here? Let's see. To the left of the y-axis, the values are less than the ones previously, but to the right, it's climbing faster and faster, isn't it? So 3 to the x climbs faster than 2 to the x because the values are tripling instead of doubling. 4 to the x, 5 to the x, 6 to the x, this thing would grow faster and faster and faster. Let's go the other direction, and that is, let's see, we'll leave these graphs on here, but now let's take a look at, let's go with green. Let's take a look at y equals 1/2 to the x power. Now, notice I've got parentheses around it, because if I wrote it like this, well, you can't, hang on here, let me move my square over here. If I wrote it like that, that x would only be on the 1. So I need parentheses around the entire base. Okay, so let's see here. So again, let's use a table of values. X, y, -3, -2, -1, 0, 1, 2, and 3. Okay, things are going to be a little trickier here. So if x is -3, y equals 1/2 to the -3 power. But that would be 2 over 1, so the reciprocal, to the +3 power, which is just 2 cubed or 8. If x is -2, y equals 1/2 to the -2 power, which is 2 over 1 to the 2 power, or just 2, to the 2 power, squared, or 4. If x is -1, y equals 1/2 to the -1 power, which is 2 over 1 to the 1 power, or just 2. 1/2 to the 0 power is 1, 1/2 to the 1 power, 1/4, 1/8. What's going on there? Well, instead of things doubling, they're halving, so to speak. Each value, as x increases by 1, y gets cut in half. It's kind of the opposite of what's going on there. So let's see what that graph looks like. -3, 8 is right here. -2, 4. -1, 2. Let's see. 0, 1. 1/2, 1/4, and 1/8. So we get this picture. Well, that's a function. It has a y-intercept at 0, 1. It doesn't have any x-intercepts. The domain is all real numbers. The range is greater than 0. But instead of it increasing, it's decreasing over its entire domain. So what we've got is a situation like this. Let's say we've got y equals b to the x. Y equals b to the x. If b is greater than 1, we have a graph that is increasing. If b is less than 1, let's see, how do I want to say this? Less than 1, it decreases. Except there's more to it than that. It has to also be greater than 0. So b has to be greater than 0 and less than 1. If b equals 1, we just get a straight line, which doesn't fit exponential equations. If b is less than 0, we get values that jump all over the place, and so that doesn't work. So basically, b, the base, has to be positive, so greater than 0, but not equal to 1. Okay, let's see here. Let's go to the next page. Actually, yeah, let's go here. And let's take a look at, let's see. Let's do y equals 2 to the x again. Okay. And this is, let's see here, what did we have? 1/8, 1/4, 1/2, 1, 2, 4, and 8. -3, 8. -2, oh, excuse me, -3, 1/8. My bad. Okay. -3, 1/8, then what? 1/4, 1/2, 1, 2, 4, and 8. So our graph looks like that. Okay. Now, what if we were to graph, do this one in red, y equals 2 to the x plus 3. So we had a constant out to the right. What would that do to the graph? Okay, well, 2 to the x would be the same as this, right? So we're just going to take those y values plus 3. So we'd have what? 3 1/8, 3 1/4, 3 1/2, 3 plus 1 is 4, 3 plus 2 is 5, 3 plus 4 is 7, 3 plus 8 is 11. Okay, so -3 is 3 1/8, -2 is 3 1/4, 3 1/2, 4, 5, 7, and 11. Well, there's an easier way we could do that. Think back to what we did with parabolas. We could just take this graph, the black graph, and shift everything up 3 units. Up 3 units, up 3 units, up 3 units, up 3 units, etc. So how about y equals 2 to the x minus 4? That would go down 4 units, down 4 units, down 4 units. So we could graph things without having to start over, just starting with this, moving it up 3, moving it down 4. How about right or left? Well, y equals 2 to the x. Again, let's go back and make it black again. Okay, so y equals 2 to the x looks like this black graph. How do we shift it left and right? By going inside the exponent. So if we had y equals 2 to the x minus 3, now that's not the same as this, okay? Here, the minus 3 is a constant, it moves it down 3 units. But here, it's part of the exponent. A minus 3 moves it to the right 3 units. Remember, inside, inverse. A plus 3 would move it to the left. Okay, that's all I want to say about that right now. But I want to go on and look at some examples of some formulas. And so, again, I'm going to pause. this. So now we're going to go back to the whiteboard screen. And let's take a look at an exponential equation. Okay. And this one says radioactive decay. All right, radioactive decay. 500 grams of a radioactive material decays according to the formula A equals 500 times 2/3 to the T power, where T is measured in years. So T is time in years. Find the amount present in 10 years, round to the nearest 1/10th of a gram. Okay, so T is time in years, and A is the amount measured in grams. Find the amount present in 10 years, round to the nearest 1/10th of a gram. So we want to put 10 in the place of T, 10 years later. All right, so what have we got? We've got 500 times, parentheses, 2 divided by 3, close parentheses, raised to the 10th power. And I'm getting 8.67067, and it goes on and on there, but it says the nearest 10th of a gram. So that would be the 10th. The 7 would round up, so we'd have 8.7 grams. Okay, now I want to look at some characteristics of this equation. They told us in the problem that they started with 500 grams of radioactive material. We could have determined that by just looking at the equation. Consider this. At the beginning of the problem, how many years have gone by? 0. So time is 0. Well, if this is 0, what is 2/3 to the 0 power? That would be 1. What is 1 times 500? That would be 500. So at the beginning of the problem, at the beginning of time, there are 500 of whatever, okay, before we even read the problem. The fact that it's 2/3 says what's going to happen. Since the base is less than 1, greater than 0 but less than 1, this thing is decreasing. It's decaying. So it's going to decrease from 500 grams all the way down to 8.7 grams over a 10-year period. But again, we can see the starting value is 500 and it's decreasing. Okay, let's take a look at another example. This says P equals 3,745 times 0.93 to the T power. Before we read the problem, what is the starting value? It's going to be 3,745, because when T is 0, this is 0, excuse me, this is 1, and 1 times 3745 is 3745. Is this thing increasing or decreasing? It's decreasing because the base is less than 1 raised to the T power. All right, now let's read it. It says, the population of North Rivers is decreasing exponentially according to the formula, which is given there, where T is measured in years from the present date. Find the population in 6 years, 9 months. All right, so if T is years, how would you write 6 years, 9 months? Well, 9 months would be 9/12 of a year, or 3/4 of a year, or 0.75. So 6.75 years would be 6 years, 9 months. So we're going to put 6.75 in for our exponent. And the population, let's see, 3,745 times, parentheses, 0.93, close parentheses, raised to the power 6.75. And let's see, what did it say to do? It didn't say to round, but they rounded to the nearest whole person. That kind of makes sense. 2294.62502. So the 6 would round up 2,295 people. Here again, the population is decreasing because the exponential part, the base, is between 0 and 1. Okay. Now, we're going to look at a special formula that's used to calculate compound interest. And the formula looks like this. A equals P times the quantity 1 plus R divided by K, all to the KT power. All right. So P is the principal. Let's see. And R is the annual interest rate. T is time in years. A is the final amount or accumulated amount. And K is the number of compoundings per year. Now, what does that mean, the number of compoundings per year? Well, how often they calculate the interest that you've earned in the account, and then that interest shows up as money in the account. So you get interest, and then you get interest on the interest, and interest on the interest on the interest. And so the more times they compound it per year, the better off the person that has the money in the bank, the better off they are. So principal is the amount you invest, and accumulated amount is what it's worth at the end of some time. Okay, so let's take this formula and apply it to some examples. All right, this one says compound interest, an initial deposit of $10,000. So the initial deposit, the principal, is $10,000, earns 8% interest. So R is 8%, which we're going to convert into a non-percent number, so a decimal number. Compounded quarterly, so K is 4. Annually, K would be 1. Semi-annually, 2. Quarterly, 4. Monthly, 12. Daily, 365, etc., etc. Okay. How much will be in the account after 10 years? So T is 10 years. And the question is, how much will there be at the end? Okay, so our formula, A equals P times 1 plus R divided by K, all to the KT power. A equals $10,000 times parentheses 1 plus 0.08 divided by 4, all raised to the parentheses 4 times 10 power. Now, there's a couple of different ways you can do this. You can put everything into the calculator just like it is. I'm going to do that. So what would I do? I go 10,000 parentheses 1 plus 0.08 divided by 4, close parentheses, then the little caret power key, parentheses 4 times 10, close parentheses. When I do all of that, I get 22080.39664. Okay. Money, well, you can't split up a penny, I guess, unless you get some tin snips. So rounding to the nearest cent, we get $22,080.40. Okay. Now, there is some simplification we could do ahead of time if we wanted to. For instance, 4 times 10 is 40. 0.08 divided by 4 is 0.02. 1 plus 0.02 is 1.02. So I could have simplified a little bit ahead of time and plugged that into the calculator. 10,000 times 1.02 raised to the 40th power, and I get the same answer. why would you do that? I don't know, just if you feel more comfortable simplifying things first. But the thing you got to be careful of, especially, is this value right there. 0.08 divided by 4 comes out nicely to 0.02. But if you get some number that isn't nice, then your tendency is to want to round it off. You don't want to round off in the middle of a problem. So any simplification that you do, if it doesn't come out to an exact number, don't do it till the very end of the problem where we round it to the nearest cent. Okay, let's take a look at another problem. It says, comparing interest rate. How much more interest could $1,000 earn in 5 years compounded quarterly if the annual interest rate was 5.5% instead of 5%? Okay, so the formula we're going to use is A equals P times 1 plus R over K to the KT power. Let's see, scenario number 1. Let's see, the principal is going to be $1,000. Time is going to be 5 years. Compoundings is going to be quarterly. Let's see here. Is that all we need? Principal. Oh, time is 5 years. The rate. Oh, the annual rate is 5%. Okay. It says, how much more interest could $1,000 earn in 5 years compounded quarterly if the annual interest rate was 5.5% instead of 5%? So our second scenario, we're going to have the same principal, the same time, the same number of compoundings, but our interest rate is going to be 5.5%, which would be 5.5% or 0.055. Okay, so everything's the same except the interest rate is 0.5% higher. Let's see what happens. Okay, so in the first scenario, A equals $1,000 times, parentheses, 1 plus 0.05 divided by 4, all to the 4 times 5 power. Okay, so let's see what I get. 1,000 times, parentheses, 1 plus 0.05 divided by 4, close it up, raise it to the power, parentheses, 4 times 5, and I'm getting 1282.037232. Okay, if this is money, I'm going to round it to the nearest cent. So to the 10th of a cent is going to round up. So $1,282.04. That's the value of the first one. Now, everything is going to be the same except the interest rate. So A equals $1,000 times 1 plus 0.055 divided by 4 raised to the 4 times 5 power. Okay, 1,000, parentheses, 1 plus 0.055 divided by 4, parentheses, close it up, raised to the power, parentheses, 4 times 5, close parentheses, 1314.066502. So that's going to round up there, and we're going to get $1,314.07. Now, the question said, how much, let's see, how much more? So we're going to take 1314.07 minus 1282.04, and we get 3203. So $32.03. Now, you might say, well, that's really not much on a $1,000 investment, but if you had a choice between two investments, the one with the higher interest rate, you'd get $32 more. Why not? But again, just to show that changing the interest rate a little bit also increases the amount of money that you would get. Okay, I've got one more example here. Again, it says compound interest. If $1 had been invested on July 4th, 1776. Okay, so the principal is going to be $1 at 5% interest. Compounded annually, so K equals just 1. What would it be worth on July 4th, 2076? Well, let's see, from 1776 to 2076, time would be 300 years, wouldn't it? Is that right? Yeah. Okay, so we want to know what it's worth. A equals P times 1 plus R divided by K to the KT power. A equals $1 times 1 plus 0.05 over 1 to the 1 times 300 power. A equals $1 times, well, this one simplifies fairly easily. 0.05 divided by 1 is going to be 0.05. So inside I'm going to have 1.05, and 1 times 300 is to the 300th power. Okay. So in $1 times that, we're going to get 1.05 raised to the 300th power. And we get 2273996.129. Rounding to the nearest cent, we'd get $2,273,996.13. Every once in a while on one of these TV shows, you see a thing where they found some old documents in an attic, a stock certificate or something, and it's like, you know, if the company's still in existence, is it worth millions of dollars? Who knows? But anyway, if this problem happened, I guess you could retire early. All right. And speaking of retiring, I'm going to retire from today's video, and I will be back at 1:15 this afternoon. Should you have any questions, have a great weekend. Bye now.